Assalamualaikum. My name is Muhammad Shakir bin Safwan. Numbers metric 250269. Firstly, I want to introduce the introduction about this report. Static is the fundamental branch of engineering mechanics that study force and moments acting to body in equilibrium when the resultant force and moment are zero. This ensures that structure and mechanical system remain stationary while safely supporting applied load, making static essential in engineering design. The engineering practice static is widely used in the analysis of structure, just as bridge, building, cranes, and tracks. Engineering apply static principle to determine support, reaction, internal force, and moments to prevent fail instability or exercise deformation. This group project applies static engineering principle to real-world problem involving force analysis, moment of couple, simple thrust and friction, depth calculation, free body diagram, and result interpolation. The project enhances understanding to practical static analysis while developing problem solving, teamwork, and communication skill essential for engineering practice. Based on the literature review, engineering static is fundamental area of the engineering mechanics that focus on analysis system in equilibrium when both the resultant force and moment are zero. According to Hibbeler, static principles such as free body diagram and equilibrium equation are essential to ensure the stability and safety of engineering structure. Previous research explained that force and moment analysis in real-world applications such as cranes, steering system, and load supporting structure. Merriam and Kerr highlight that the moment of the couple produced per rotation without translation, which is important in mechanical control system. In structure application, McMorcom and Nelson state the simple thrust efficiently distribute load through tension and compression, reducing a material use and structure failure. Overall, the literature supports the importance of static engineering principle in activist safe, edges, and rebuild engineering design which directly support the objective of the project.
Hi, my name is Muhammad Amir Hakim bin Azhar. My matrix number is 250252 and I will present about problems faced in a real world. So, the first is friction. So, the problem faced in the world, the real world problem is screws holding objects together. So, why? Because of friction keeps screw tight between materials. For example, screw fastening to pieces. And for the engineering theory, for the friction is friction in screw, relationship between axial force and applied torque. Second is balancing a seesaw. The real world problem because of placing the fulcrum to balance people of different weight. For example, is seesaw used by two people, center of gravity and fulcrum. So for the theory is center of gravity, point where the total weight of an object acts. Third is force. The real world problem is force on a crane. So engineers must account for load weight, crane weight, wind force, and boom angle. For example, crane lifting a load. For the engineering theory is static. Use equilibrium principle to keep crane stable and prevent tipping. And second last is moment of a couple. So the real world problem is steering wheels. Turning a car requires a couple equals and opposite forces applied to the wheel. For example, when someone turning the steering wheel. For the engineering theory, moment of a couple, two equal, opposite, non-collinear force create a rotational moment. And the last is simple truss. Real world problem is roof truss. Description. Roof trusses are used to support the weight of a roof over a wide span. For example, roof truss to support a beam. Method of joint. Analyzing forces at each joint to determine member force. Method of section. Cutting through members to analyze forces.
Assalamualaikum, my name is Muhammad Arif Mikael Bashar Afzan. My metric number is CD250140. Today, I will present to you about our first choice of real world problem, that is force. As you can see from this question, we have given a car that weight around 3,500 pounds is being carried onto a ship using two types of rope and on a crane. From this question, they intend us to find the tension in every ropes. As you can see, this is the solution I propose. That is using equilibrium style of calculation. First, we find our fx and fy. Then we create a question to eliminate the unknowns. As you can see here, I get our T is equal to 15275.8 Newton. Then after we get our unknown, we move to step 4, that is to eliminate the remaining unknown. As you can see, I use R equal to T sine 2 per cos 30. We have our T as a solution, so we can get our R, that is 613.30 Newton. Now for the discussion and result. Cable and tension. The cable carries a large tension of 15278.5 Newton, showing that it's mainly support the weight of the vehicle, the weight of the 3,500 pound of automobile. The tension is slightly lower than the vehicle weight because a small part of the load is supported by the vertical component of the rope. Next is the rope tension. The rope tension is much smaller at 615.30 Newton. This is because the rope is used mainly to keep the automobile centered horizontally, not to support its weight. The 30 degrees angle allowed the rope to balance the small horizontal force from the cable. Equilibrium condition. The system remains stable because all forces are balanced. The horizontal force of the rope balances the horizontal force of the cable, while the vertical component of both tension support the automobile weight. And lastly, the practical implication. A strong cable is required due to the high tensional it carries. The rope must also be strong enough even though tension is smaller. The angles of the cable and the ropes are important. Changing them will affect the tension and the system stability. That's all from me. Thank you.
Assalamualaikum. My name is Amir Zulkhairi bin Muhammad and my matrix number is CD250271. Next, I will present the second of the real world problem, what witches. Our scenario involves a driver applying a pair of 25 Newton force to a steering wheel with a diameter of 318 mm. To find the magnitude of the moment, we multiply the force by the distance. which give us a total moment of 9.5 Newton meter. However, because the steering column is inclined at a 20-degree angle from the vertical axis, we need a more precise vector representation. We define the position vector for a point A and B using trigonometric component, specifically 0.785 in the J direction and 0.065 in the K direction. By calculate the relative position vector between these 2 points, we get a displacement of 0.357 J and negative 0.130 K. Finally, to find the moment vector, we perform a cross product of this position and our 25 Newton force. This calculation reveals that the moment is not just a single number, but a vector acting into plane, negative 3.25 J and negative 8.93 K. This breakdown is exactly what allows us to understand how the torque resolves into a dashboard and the steering column assembly. Next, for the result and discussion, let's start with what actually happens physically when you turn the wheel. The most significant finding is that we are not just applying force, we are creating a pure couple. In engineering terms, this means the 9.5 Newton meter moment act as a free vector. Because it's a pure couple, the steering column feels the exact same amount of torque regardless of where your hand and on the rim, whether you prefer the 10 and 2 position of 9 and 3, as long as your hand maintain the 380mm spacing. The steering response is identical. This is a key part of driver ergonomics. It ensures the car feels predictable and consistent for every driver. Now, how does the force actually travel into the vehicle hardware? To visualize this, we use the right hand rule. If you curl your finger in the direction of the steering turn, your thumb point exactly where the moment vector is headed, straight down and axis of the steering column. Our calculation gave us specifically negative component. This is not just abstract data. It tells us to torque is pushing down and away toward the dashboard. As an engineering, you will use the specific vector data to select the right bearing. We need bearing that can handle not just the twist of the turn, but the specific angle and thrust of the steering column. Finally, let's look at the practical design requirement. While 9.5 Newton meter might seem like a small number, it's our fundamental load case. We use the value to calculate torsion stress to ensure the steering shaft diameter is thick enough to avoid snapping or permanently twisting during a sharp turn. However, we have to account for the real world. In our math, we assume a pure couple with two hands, but we know drivers often use just one hand. That shift changed the physics from a simple twist to a bending moment. Because of this, our final safety margin must be even higher than our perfect calculation to ensure the shaft can handle the extra side loading. That's all for me. Thank you.
Okay, so I will explain about the simple thrust as we can see at this diagram. So the question, in a truss-based structure, repeated problems have been observed where certain members experience excessive bending under load. As a result, structural failure may occur at these critical members. As an engineer, you are required to analyze the truss system to identify the magnitude of the load acting on each members at the joint. Based on this analysis, determine which members carry the highest load, and the engineer can choose the most suitable material to be used for the truss bridge to safely withstand this load without excessive bending. So from this question, we need to identify the members that have highest load. So we can help engineer to find the to choose the suitable material. So this is the calculation of the truss. First, we need to find the reaction force using moment equal 0. So at moment A, we can get the value of Ay equal 30 kilonewton. And if we find the moment at moment E, we can get the value of Ay is 30 kilonewton. And then we make a free body diagram at the left section. We can get the answer of FDC equal 30 kilonewton, for FFG negative 30 kilonewton, and FFC we can get the value is 42.43 kilonewton. And then we make the free body diagram at the left section. We can get the answer of FBC is 30 kilonewton, for FFG is negative 30 kilonewton, and lastly for FHC is 42.43 kilonewton. So so from this we can know the highest load at FFC and FHC. And lastly, the result of discussion. The 45-degree truss geometry allows force to be transferred efficiently and ensure the structure is in static equilibrium. The design is efficient because most members carry tension or compression with minimal bending, making the bridge lighter and safer. Some members experience higher force due to their position, so they must be designed stronger to prevent failure. From the calculation, we can identify which members need to use strong material. The calculations show the FC and FH has higher pressure, so the engineer can choose the suitable material.
Okay, for the conclusion, in conclusion, the literature reviewed clearly show that engineering statics is essential for understanding and analyzing systems in equilibrium. Principles such as force balance, moment of a couple, thrust analysis, and friction play a crucial role in ensuring the stability, safety, and efficiency of engineering structures and mechanical systems. The studies highlight that applying these concepts in a real-world situations such as crane, steering mechanism, and truss structures help engineers prevent failure, reduce material usage, and improve overall design reliability. Therefore, static engineering principles provide a strong foundation for safe and effective engineering practice, supporting the objective of this project. So, that's all from us. Thank you.